Now I'd like to welcome to the screens virtually Pamela Mauser-Boss.
Thank you. This is something I've puzzled over for a number of years, and so I'm going to present the evidence, discuss our investigation, and we'll see if you think we solved the case. Now, I know of 4 groups who have done co-deposition and have looked for tritium, and Bocker's was one of these. He used an open system. He plated on a gold cathode that had a concentric orientation with the platinum anode. His plating solution was palladium chloride and lithium chloride. He used both low and highly tritiated D2O, and he had a separate chamber where he recombined the gases so he could measure the tritium in both the gas and liquid phases. And what he found is that when he had low tritiated D2O, he saw bursts of tritium greater than what he expected from enrichment from the electrolysis. But when he used highly tritiated D2O, he saw a loss of tritium. Miles also did some experiments again, with both bulk palladium samples as well as the co-deposition. He also had an open system. He plated on a copper cathode that was in a concentric orientation with his anode, but instead of the lithium chloride plating solution, he used ammonium chloride and ammonium deuteroxide, and he was hoping to produce a smooth palladium bright deposit. However, it ended up being dark and dendritic. He used only highly tritiated D2O, and what he did is at the end of his experiments, he adjusted the volumes back to what he had initially and measured the tritium before and after. And you can see here's his tritium measurement before. You see his measurements for his bulk electrodes, and you see there's an increase in tritium, which he attributed to enrichment as a result of the electrolysis. But for his co-deposition cells, which, by the way, produced excess heat, you see that there's a net loss of tritium. We did a similar experiment as Bocker's. We had an open system. We plated on a silver-coated copper cathode, again, a concentric orientation with the platinum anode. We had a catalyst in a separate chamber to recombine the gases so we can measure the tritium content in both the gas and liquid phases. We used a palladium chloride, lithium chloride plating solution, and we did 5 experiments. 2 of them showed a complete mass balance as shown here, but 3 of them did show bursts of tritium here and here, and whenever we had a burst of tritium, it was a production rate of 3,000 to 7,000 atoms per second. A few years ago, Lee at the conference in South Korea reported on their co-deposition tritium results. And they used a closed system. So they measured the tritium before and after. They plated on a nickel cathode that was in a parallel arrangement with the platinum anode. Their electrolyte was palladium chloride and lithium chloride, or they also had another one where they complexed the palladium with ethylene diamine. And they used both low and high tritiated D2O. And here are the results. You can see for the highly tritiated, at the end of the experiment, there was a significant drop in the tritium. And for the low tritiated, they saw an increase. So 4 groups conducted experiments measuring tritium in the co-deposition process. In each experiment, the palladium deposit was black and dendritic, so it had a high surface area. Different plating solutions were used, different cathodes were used, but regardless of this cathode substrate and plating solution, tritium production was observed when low tritiated D2O was used, but when high tritiated D2O was used, a decrease in tritium was observed. And this decrease suggests that there's some nuclear reaction or reactions that are consuming the thermal tritium. Well, it's a pretty simple system, so we decided to look at the nuclear reactions between tritium and solution components, as well as reactions between tritium and nuclear generated particles. So first, lithium and palladium isotopes in tritium. Well, there are no cross-sections reported for palladium and tritium, so this is unlikely to happen. We know that lithium can interpolate into the palladium lattice, and there's a number of nuclear reactions that occur between tritium and the lithium isotopes. But the cross-sections are in the millibarns. The ones I'm showing here are the largest ones. But unfortunately, Miles still observed a decrease in tritium, and he did not have any lithium salts present. And also, both with regards to lithium and palladium, the tritium reaction would be involved energetic tritons, not thermal. So it's unlikely that the palladium and lithium isotopes are involved in the loss of the tritium. So then we looked at possible nuclear reactions between tritium and hydrogen and helium isotopes. And here we showed cross sections as a function of energy and tabulated the maximum cross sections. And we can rule out the tritium alpha particle reaction immediately because that's in the microbarn region. But we see that DT reaction has a really high cross section, 5 barns, and we have seen evidence of the neutrons from the DT reaction, and that's with our triple tracks. When a neutron with an energy of 9.6 MeV hits a carbon atom, it causes it to shatter into 3 alpha particles, and there's 5 different reaction pathways for the carbon breakup to occur. And we have not seen any triple tracks in either blank CR39 or CR39 used in control experiments. So I'm thinking, we got the culprit. But Peter says, not so fast. For DT fusion to occur, the tritium has to have an energy greater than or equal to 5 keV. And he's correct. The DT reaction will only work with energetic tritons. But is there a way we can overcome that 5 keV energy requirement so that thermal tritium can be consumed? Can electron screening help us? Well, there's been several talks already on electron screening effect, but I have tabulated here the screening potentials for various palladium species. And we see that with lithiated palladium, we get some pretty sizable electron screening potentials. However, Mel Miles did not use lithium salts, and he still saw a decrease in tritium. So unfortunately for us, the DT reaction is not responsible for the loss of thermal tritium. So we then looked at the TT and T helium-3 reactions. In the TT reaction, both energetic and thermal tritons will be consumed. For the 1 MeV triton, the cross section for the reaction is 89 millibarns, which isn't too bad. And what's really helpful for the TT reaction is that 1 MeV triton can go through 5 microns of palladium deuteride, or about 12,000 units cells. So that's a good chance of running into somebody. But it's, it might be contributing, but it's probably not the main reaction responsible for the loss of our tritium. So then we look at the tritium helium-3 reaction. And the energetic helium-3 would be formed from a DD reaction, which can then react with a thermal triton. So the thermal triton will be consumed. The cross-section is pretty decent, 189 millibarns, 4.82 MeV helium-3. But it can't go through much palladium deuteride. It only can go through about a micron, and that's only about 2,800 unit cells. So the likelihood of finding a thermal triton isn't so great. But it does form this energetic deuteron, which can go and feed back and continue the reaction going. But it's unlikely that it's the main reaction responsible for the loss of our tritium. So that brings us to the PT reaction. And SRI did a really nice replication of our results of our experiments with CR39. The CR39 detectors underwent extensive analysis. Lipson and Rosetsky did a sequential etching analysis and identified 3 MeV protons. Zhao went and analyzed the scan data that we had, and he identified a continuum of alpha particles and protons ranging in energy from 3 to about 14 MeV. It's not continuous. There are some troughs observed here indicating that these protons are being consumed. For a 3 MeV proton, the cross-section of the PT reaction is 600 millibarns, which is really pretty good. And what's really good is that it can go through 34 microns of the palladium deuteride, which would encompass about 84,000 unit cells. So it's good odds of encountering triton. And the 14.7 MeV proton will traverse 433 microns of palladium deuteride, which is over 1 million unit cells. So we believe that the PT reaction is the likely culprit for consuming our thermal tritium. So in conclusion, using co-deposition, 4 research groups conducted experiments measuring tritium. It was shown that regardless of the plating solution or cathode substrate employed, the tritium production was observed with low tritiated D2O. However, a loss of tritium was observed when highly tritiated D2O was used. We looked at cross sections of tritium with palladium, lithium, helium-4, and deuteron, and either because of the requirement that they consume energetic tritons, not thermal, or the cross sections were too low, we concluded that these species were not involved in the consumption of the tritium. And again, based on the cross sections and how far the charged particles can go through the palladium lattice, we concluded that the PT reaction is primarily responsible for the loss of the tritium, although the TT and T helium-3 reactions are minor participants. And I'd like to point out that this tritium loss is not observed for bulk palladium, suggesting that the consumption of the thermal tritium is related to the high surface area of the palladium deposit, or it could be due to the vacancies present in the lattice, which allows for more than 2 deuterons to occupy a site in the lattice. We'd like to thank all the research groups who have conducted tritium measurements using co-deposition. Thank the SRI group who replicated our CR39 results, as well as Frank Gordon and Dr. Kim for their support. And of course, we have to acknowledge the contributions of the late Stan Schwach for conceiving and developing the co-deposition process. Thank you.
We have time for about 1 or 2 questions. Go ahead.
Okay, I don't understand why you compare different reactions at or cross sections of reactions at very high energies. So you should do it for room temperature cross sections, because if you have deuteron and you measure tritons, so the main mechanism to produce tritons is this DD reaction. So it is very simple, and it is something what we understand very well. And if you want to destroy tritons, it is next D plus triton reaction. It is, on the one hand, you produce some tritons. On the other hand, you reduce the number of tritons. So it is very easy to calculate, and I think it can be explanation for your results.
Well, I've pointed out that we have evidence of producing the energetic protons in the...
But the number of protons is very low, but the number of deuterons inside of your sample is very high. Therefore, the reaction rates are proportional to the number of included particles. It is even the square value of that. So this is the largest number, largest factor that decide about the nuclear reaction rates.
Well, we'll take your comments in consideration.
Thank you.
All right, Pamela, thank you very much.